Today we're doing some more Calculus 2 practice problems looking at Taylor and Maclaurin polynomials. This is a bit of a different direction than the last few videos. In the last few videos we looked at different tests to determine the convergence or divergence of infinite series. But this is related because we'll be looking at Taylor and Maclaurin series in a few videos. So before we do that, we need to know how to deal with the Taylor and Maclaurin polynomials. So these are approximations of functions. For example, if we have sine x, we can build a polynomial that looks like this. It might look something like, it can be high degree polynomial, and we'll look at it, and as we add in more terms, it will give a better approximation about a certain point. So for example, with just one term, it might give just a linear approximation of sine x about the origin. And then as we add in more terms, it will encompass more and more of the sine x function. That might be with two terms, right? It'll be a polynomial that looks like this. And as we add in more and more terms, it'll grab more and more of the curve of sine x or other exponential kind of functions centered about a certain point. So what is the difference between a Maclaurin and a Taylor polynomial? Well, a Maclaurin polynomial is a Taylor polynomial that is centered about the origin. So it has this form. We take f, our function evaluated at 0, add that to f prime of 0, and increase the derivatives, right? First derivative, second derivative, third derivative. And then in the second term, we add in an x, and an x squared, and an x cubed, right? And then we also start dividing by the factorial, that nth factorial. So the nth Maclaurin polynomial is just the nth derivative evaluated at 0, of course added to all the terms before this nth term, times x to the nth power divided by n factorial. So we could call this n equals 0, n equals 1, n equals 2, which means this one is actually divided by 0 prime, and this one's divided by 1 prime, but 0 factorial and 1 factorial. But 0 factorial and 1 factorial are just 1, so they don't really show up. But as you can see, triple derivative, triple power, triple, or third derivative, third power, third factorial, right? So a Taylor polynomial is the same thing, except it's no longer centered about 0. We don't have a 0 there. We have c. It's centered about c. And so we have c, f prime of c, x minus c instead of just x. So f double prime of c, x minus c squared. So second derivative, second power, and 2 factorial, right? So it's the same thing, except it's not centered at 0 anymore. It's centered at some c. So this is a much more general form. So a Maclaurin polynomial is just a Taylor polynomial that is centered about the origin. So we're going to be using this form, right? For example, if they ask us to find the Maclaurin polynomial for f of x equals e to the negative x, n equals 5. So what does that look like? That looks something like this. E to the negative x kind of looks something like this. It's the exponential function, but reflected about the y-axis. So what we're going to be able to do is we're going to be able to find a first degree approximation that might look something like that. But since they tell us that n equals 5, we're going to find a fifth degree approximation, and that's going to be very accurate. It might look something like this, but then of course it will branch off the polynomial. Since it is a Maclaurin polynomial, it is centered about 0, so it's going to be most accurate near x equals 0. So let's see if we can remember the form. P sub 5 of x will equal f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared plus f triple prime of 0 times x cubed. This one's divided by 2 factorial. This one's divided by 3 factorial. Since we're going all the way to n equals 5, may as well just put fourth derivative evaluated at 0 times x to the 4 over 4 factorial. And finally, the fifth derivative of our function evaluated at 0 times x to the 5th power divided by 5 factorial. So we need a few things, right? We have that f of x equals e to the negative x. We need f of 0, f prime of 0, f double prime of 0, f triple prime of 0, the fourth derivative of our function evaluated at 0, and finally the fifth derivative of our function evaluated at 0. So plug in 0, you get e to the 0, which is just 1. What's the derivative? The derivative is just negative e to the negative x, because the chain rule brings a negative out front. But the second derivative brings us back to a positive, because we bring out another negative. Two negatives make a positive. So it's just switching between this and this. So when we plug in 0 into this function, we'll just get negative 1. Plug it back into the first function, 1. Back into the other function, negative 1. It's just alternating between 1 and negative 1. Also, what is 2 factorial, 3 factorial, 4 factorial, 5 factorial? That's 2, 6, 24, and 120, right? Because you multiply by 3 to get there, by 4 to get there, and by 5 to get there. So now that we have everything, we can just put it into our polynomial, right? We have p sub 5 of x equal to, what was f of 0? 1, plus f prime. F prime was negative 1 times x, so we'll call it negative x. And then we had, now we're here, right? We have plus the second derivative of our function evaluated at 0, which was 1, times x squared divided by 2 factorial. So that would be plus 1 times x squared divided by 2, minus x cubed over 6 plus x to the 4 over 24. So once again, x to the 4, the fourth derivative evaluated at 0 for us was 1. So here's a 1 right here that I didn't put, times x to the 4, which is y, which is x to the 4. And we're dividing by 4 factorial, which was 24. Finally, for the last term, it will be this. So this is a very good approximation of e to the negative x. If you plug both of these into your calculator, your graphing calculator, and you graph them, there will be a considerable overlap between the two until, like I said, our polynomial runs out of accuracy and shoots back up like a polynomial would. So that is how we use a Maclaurin polynomial to approximate a curve about, or for 5 terms. So this is the answer. So, for example, maybe you don't remember how to integrate e to the negative x, but from like 0 to 1, right? But this polynomial right here and e to the negative x will pretty much have the same exact graph from 0 to 1. So in some cases, it'll be easier to integrate our Maclaurin or Taylor approximations, and you should get the same answer because it is a matchup. So let's look at now finding the polynomial to approximate f of x equals 1 over x squared when n equals 4, c equals negative 2. So this is no longer a Maclaurin polynomial because now we are centered at a different point, right? So p sub 4 of x, let's just write it out. It would be f of 0, no, not 0, f of c. And what was c? Negative 2. So f of negative 2 plus f prime of negative 2 times x, not just x, but x minus c. X minus negative 2 is the same as x plus 2, plus f double prime of negative 2 times x plus 2 squared, all over 2. Two more terms, we have a triple prime over 6, and finally our fourth derivative to the 4th power over 24. So this is our polynomial, which means we need to find a few things. F of x, we need f prime of x, we need f double prime of x, the third derivative of x, or of our f of x, and finally the 4th derivative. And then we need to evaluate all of those at negative 2. So f prime of negative 2, f double prime of negative 2, f triple prime of negative 2, finally the 4th derivative of our function evaluated at negative 2. So let's see, what was f of x? F of x is x to the negative 2, which means the derivative of that is negative 2x to the negative 3, and 6x to the negative 4, and negative 24x to the negative 5. Finally, 120x to the negative 6. So this will be 1 over x squared, negative 2 over x cubed. I just like to write it like this so it's easier to plug in. 6 over x to the 4, negative 24 over x to the 5th power, and finally 120 over x to the 6. Now let's plug in negative 2. We get 1 over negative 2 squared, so you just get 1/4. We get negative 2 over negative 2 cubed, so that should just be 1/4 again. And we can repeat this process. This one would be 6 over negative 2 to the 4th power, which is 16. 6 over 16 is 3/8. And we will repeat these for the last two and just get 3/4 and 15/8. So now that we have all of our f parts, we can just set up the polynomial. So we could say that the fourth Taylor polynomial of x centered at c equals negative 2 would be f of negative 2, 1/4, plus f prime of negative 2 times x plus 2. And then we have 3/8 x plus 2 squared divided by 2, right? So I'm going to just write that as 3/16. And you repeat this for the rest of the polynomial, and you should get 3 divided by 4, but then we're going to divide by 6, which is 3 factorial. And our final term would be 15 over 8, but then we're dividing 8 by 24, right? And 8 divided by 24, or 8 times 24, is 192. So I have that x plus 2 to the 4th power. So whatever 1 over x squared looks like, it looks something like this, if I remember back to college algebra correctly. And we're centering it about negative 2, which means our polynomial probably looks something very similar to this. So we have a pretty good approximation about this point, c equals negative 2. So if you want to evaluate this at negative 2, the y value you get will be something similar to this one, right? So that is how we do. Or you can see that when you plug in negative 2 into our function, remember we got 1/4. And then when you plug in negative 2 into our approximation function, all of these terms will drop out and you'll still be left with 1/4 because it is the most accurate at that point, right? So that is how we do Taylor polynomial. Let's look at one more example. Finding the polynomial to approximate f of x equals sine x at the origin, but n equals 10. Is that going to be an issue? So I'll just write it out. P10x equals f of 0. This is a Maclaurin polynomial, right? Because we're centered about the origin, or x equals 0. So f of 0 not equals plus f prime of 0x plus f double prime of 0 times x squared, dot, 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 all the way till we get to the 10th derivative valued at 0 times x to the 10 over 10 factorial, right? So obviously this is going to take way too long to do it in the same strategy, so we're going to try and find a pattern. For example, f of 0 equals sine of 0, which is 0. F prime of 0 equals cosine of 0, which is 1. F double prime of 0 equals negative sine of 0. Make sure I'm doing that right. Cosine of 0, derivative of cosine is negative sine. Plug in a 0 into negative sine, you'll get 0. Triple derivative, you're just going to get negative 1. And this pattern will repeat itself. We'll go 0, 1, 0, negative 1. 0, 1, 0, negative 1. Okay, so let's see what we can do. It looks like this term and even our last term here, right? When n equals 10, that term all gets dropped out. So we're just left with all the even ones, and every other one is negative, right? If we were to put right here the triple derivative, remember what our third derivative was? It was just -1. So it looks like we have a pattern here. We're left with x minus x cubed over 3 prime plus x to the 5th over 5 prime minus x to the 6, not 6 because all the even ones got knocked out, x to the 7 over 7 prime plus x to the 9 over 9 prime. So we can use a bit of a shortcut. We can see that all of the even ends, right? This was n equals 0, n equals 2, n equals 4. So all of the even ends in the 0, 1, all ended up being 0, so that term just gets knocked out. So we're left with just odd n powers, right? 1, 2, or 1, 3, 5, right? Here's 1, 3, 5. And they're alternating between positive, like this one's positive, negative, positive, negative, positive. So we can approximate this even all the way up to, n equals 20, n equals 30. The only issue is evaluating that 9 factorial is a giant number, right? So once you get to a certain point, you're not really adding anything effective in, because 9 factorial is 300,000. So eventually we're just approaching infinity at that point. No matter what you plug in for x, no matter how big it is, if you're dividing by 362,000, you are, like, this term will just drop to 0 because we can treat the bottom like infinity. So this would be I'm not going to evaluate factorials, but this would be the Maclaurin/Taylor polynomial to approximate sine x. So finally, remember, like we did at the beginning, sine x kind of goes like this, and our function will match it for a little bit, not forever, maybe something like this, and continue on. Centered about 0, that is. So that is how we use Taylor and Maclaurin polynomials to approximate functions. And we'll look at how we can integrate these into, not integrate them, but how can we use them with series.